Just like people, military aircraft have their own unique lifespans. Some airframes live incredibly long lives. They are constantly getting upgraded and spawning entire families of new variants. Others never even get a chance to truly stretch their wings and enter service, and instead they end up permanently grounded as museum exhibits. That is exactly the sad fate that befell the ambitious British TSR-2 strike aircraft. The story of the TSR-2 begins back in March 1957. That is when the Royal Air Force issued a highly demanding set of requirements. They wanted a new aircraft to replace the aging Canberra bomber. For the late 50s, the concept was incredibly bold. The RAF wanted a bomber capable of sustained supersonic flight, reaching speeds well over 1,000 miles per hour. This was needed not just at high altitude, but right down on the deck. On top of that, the aircraft had to be all-weather, feature massive range, and be capable of delivering tactical nuclear weapons. Another absolute must was the ability to operate from unprepared dirt strips. This meant it needed short takeoff and landing, or STOL, capabilities. As for the reconnaissance variant, they planned to pack it to the brim with the most advanced avionics available. But British designers had barely gotten a look at these specs when dark clouds started gathering over the project. The first major red flag was the infamous Defense White Paper. It was published by Minister of Defense Duncan Sands in April 1957. In it, Sands boldly declared that the era of manned combat aircraft was over. He believed the future of warfare belonged entirely to guided missiles. Because of this, the government decided to completely pivot its military strategy. They funneled almost all available funding directly into missile programs. In hindsight, the missile obsession of that era turned out to be a monumental strategic blunder, and not just for the British. The Soviet Union and the United States managed to shake off the fallout of their political leaders' missile craze within a few years. They quickly got back to developing combat aircraft. Britain, however, never fully recovered from this severe blow to its domestic aviation industry. Getting back to the late 50s, the developers' next major hurdle was fighting their own government. Politicians stubbornly tried to force a different strike aircraft onto the Air Force. This was an airframe that was currently in development for the Royal Navy. This aircraft would later become famous as the Blackburn Buccaneer. The RAF tried to explain that the Navy Buccaneer was strictly a transonic aircraft. It was designed for a completely different mission profile. But at first, those arguments fell on deaf ears. The situation only got worse when Blackburn started promising they could build a supersonic version of the Buccaneer. Ultimately, Air Force Command had to draft exhausting, detailed reports for the bureaucrats. They needed to prove exactly why a naval strike fighter was totally unacceptable for their needs. The main reason for their pushback was simple. No amount of upgrades would ever allow the Buccaneer to hit Mach 2, or roughly 1,400 miles per hour. The Air Force, meanwhile, desperately needed exactly that kind of high-speed, low-level strike and recon platform. After much debate, development of the new aircraft was finally greenlit. The ministry set a strict deadline. All design proposals had to be submitted by the end of January 1958. Of all the proposals submitted, the designs from English Electric and Supermarine stood out as the most promising. Early on, English Electric was considered the clear frontrunner. However, their competitors had a major ace up their sleeve. For the first time, they proposed treating the aircraft not just as an airframe, but as a complete integrated weapon system. From the ground up, this concept included all the ground support equipment needed to maintain the aircraft and sustain combat operations. For a long time, the selection board could not pick a winner. A major reason for this was that the British government was actively pushing to consolidate the aviation industry into huge conglomerates. Because of this, forcing both contractors into a joint project seemed incredibly appealing to the politicians. To force the engineering teams to collaborate, the ministry issued an updated specification. Under these new requirements, the first squadron was expected to take delivery of the aircraft by the end of 1965. These incredibly tight deadlines caused near panic among the design teams. But by early January 1959, the dust had finally settled. The military officially greenlit full-scale development of the aircraft, designated the TSR-2. As a nod to its lineage, the project's predecessor, the English Electric Canberra bomber, was retroactively and fittingly dubbed the TSR-1. But the true grandfather of this whole tactical strike and reconnaissance concept was considered to be the legendary Fairey Swordfish biplane. To put it mildly, both manufacturers were far from thrilled about the forced marriage. Each had its own deeply rooted corporate culture and manufacturing processes. These now had to be completely overhauled to make the partnership work. A major issue popped up right away. Where exactly were they going to build and test the first prototype? Vickers insisted on using their facility at Brooklands, even though the local airfield was too short and ill-equipped for flight testing. English Electric, on the other hand, was pushing hard for their own facility at Wharton. Their plant and airfield were already perfectly set up for building supersonic aircraft. After all, that is where the famous Lightning Interceptor was currently in production. This was a fighter capable of hitting speeds over 1,400 miles per hour. To avoid a complete stalemate, both companies eventually compromised on neutral ground. This was the military test facility at Boscombe Down. Granted, they would end up revising this agreement a short while later anyway. The bickering finally came to an end in June 1960. That is when a historic merger took place. Vickers Armstrong, English Electric, and Bristol Aeroplane combined to form an aerospace giant called the British Aircraft Corporation, or BAC for short. The workload for the new aircraft was split among the three companies in a 40, 40, and 20% ratio, respectively. By early October of that same year, the newly formed corporation secured a massive contract worth 90 million British pounds. For that money, they were expected to build 9 development airframes. Down the line, the plan called for another 11 pre-production aircraft for final operational testing. The financial side of this project was a tremendous burden that constantly hung over the developers. Ultimately, it was one of the main reasons the entire program collapsed. Development estimates just kept climbing. By the end of 1962, the projected total cost had jumped to a staggering 175 to 200 million pounds. The unit cost for a single jet shot up to over 2 million. At the same time, deadlines kept slipping. The development team was now aiming for the end of 1967. By June of the following year, the total estimated cost of the program had ballooned even further, hitting 222 million pounds. In a desperate bid to cut costs, it was proposed to slash the aircraft order. The numbers would drop from 138 down to 50 or 60 airframes. But Royal Air Force Command flatly rejected the idea. Still, the British top brass frantically looked for ways to save the program. For instance, the Minister of Defense proposed 2 alternative options to help offset the financial bleeding. First, exporting the brand new TSR-2 to the United States seemed entirely realistic. After all, the British Canberra was already flying successfully stateside, being built under license as the Martin B-57. Second, the minister suggested using the new jet as more than just a tactical strike bomber. A bold idea emerged to equip it with heavy standoff missiles. This would turn it into a full-fledged strategic platform. In reality, however, both of these options were complete non-starters. The Americans were already well underway developing their own F-111. With that project looking incredibly promising, they simply did not need a British aircraft. Meanwhile, the idea of arming the TSR-2 with the existing Blue Steel standoff missile failed miserably. This weapon was originally created for the Heavy Vulcan and Victor Phi bombers, and it was just too massive for the new airframe. Developing a brand new air-launched missile from scratch was completely out of the question. This was especially true for a bomber that was already blowing a gaping hole in the budget. Furthermore, the minister's proposal to arm the bomber with weapons like the American Bullpup missile for strategic strike missions was deemed downright absurd. It completely exposed his lack of understanding of air combat. The effective range of those missiles was only about 5 nautical miles. The only real ray of hope came from a surprise visit by a delegation from the Royal Australian Air Force. After taking a close look at the aircraft's development, they expressed a serious intent to buy 24 airframes. But eventually, even this last lifeline vanished. The Australians changed their minds and bought the American F-111 instead. So, what about the actual aircraft at the center of this story, the one that sparked so many fierce debates? Looking back, it was a classic example of a third-generation combat jet. The airframe incorporated practically all the best aerospace engineering achievements of its era. Its aerodynamics, Powerful twin engines and advanced avionics were a prime reflection of the cutting-edge technological trends of the early 60s. In terms of design and outward appearance, the TSR-2 bore a strong resemblance to the American A-5 Vigilante carrier-based strike aircraft. This plane was just entering service at the time. It also resembled the Soviet T-6-1 prototype, as became clear much later. The jet featured a highly elongated fuselage, a shape considered ideal for maintaining stability at high supersonic speeds. Its trapezoidal, 60-degree swept wing also had a fascinating feature. It had slightly downturned wingtips. This engineering solution not only improved the aircraft's stability in the air, it also generated additional compression lift when pushing past Mach 1, the speed of sound. The heart of this ambitious project was a pair of powerful Olympus engines. Essentially, these were upgraded, afterburning versions of the exact same power plants already successfully flying on the iconic Vulcan bomber. However, even this cautious approach of relying on a proven design did not save the developers from serious technical issues. In December 1963, disaster struck. During routine taxi testing, a Vulcan flying testbed fitted with the new engine suffered a catastrophic explosion. The cause was later traced to a turbine that had entered a destructive resonance. The setbacks continued in July 1964. A main engine shaft failed and shattered to pieces during a ground run on the test stand. Despite those early teething problems, the new Olympus engines left their predecessors in the dust when it came to sheer thrust. To give you an idea of their capability, the heavy Vulcan testbed could easily maintain level flight using just a single new Olympus engine. This was done with all four of its standard engines completely shut down. And as a quick side note, this engine was destined for a much longer and more famous career than the aircraft it was actually built for. These same mighty Olympus engines would eventually power the legendary Concorde. Since the TSR-2 was designed to fly long distances at high speeds, engineers crammed fuel into virtually every inch of available space. They packed 4 massive tanks into the fuselage. 2 of these sat directly over the scorching hot engine bays. They also added integral fuel tanks built straight into the wings. The total capacity of this huge fuel system was just over 6,700 imperial gallons. This translates to just under 54,000 pounds of fuel. That is a seriously impressive figure for a tactical strike aircraft, especially since it had a maximum takeoff weight of nearly 96,000 pounds. Fuel burned off during flight, which could shift the center of gravity. To keep the aircraft balanced, an automated system developed by Lucas constantly transferred fuel between the tanks to maintain optimal trim. To extend its range even further, an in-flight refueling probe was mounted on the left side of the forward fuselage. It was placed right near the cockpit. To get such a heavy aircraft to take off and land properly, the designers incorporated a highly effective aerodynamic setup. They ran full-span, 2-section flaps across the trailing edge of the wing. These were integrated with a complex boundary layer control system. This system is also known as blown flaps. The engineers saw this as a much simpler and lighter alternative to variable geometry. They preferred it over the swing wing designs that were becoming wildly popular in the early 1960s. For takeoff, the flaps would drop to 35 degrees. For landing, they would be set all the way down to 50 degrees. According to engineering calculations, this setup gave the aircraft a very short takeoff roll. It required just over 1,600 feet at a normal gross weight. Now, to bring this beast to a quick stop after touchdown, they utilized 4 large speed brakes. These were mounted on the aft fuselage, right between the wing and the tail section. Interestingly enough, the wing itself did not have conventional ailerons at all. Instead, roll control was handled entirely by the horizontal stabilizers. They operated differentially, deflecting in opposite directions to roll the aircraft. This setup is commonly known as tailerons. Overall, the tail section of the TSR-2 was pretty groundbreaking for its time. It featured an all-moving vertical stabilizer along with all flying horizontal stabilators. These were actually fitted with their own geared elevators. This provided even more precise and smooth flight control. They designed the landing gear knowing this aircraft would have to operate from rough, unprepared airstrips. The nose gear featured a completely unique mechanism. Right at the very end of the takeoff roll, the strut would automatically extend. This would pitch the nose up sharply. It increased the angle of attack and helped the bomber get airborne that much faster. Additionally, all the wheels were fitted with special low-pressure tubeless tires. This kept them from bogging down in soft ground. The main landing gear featured tandem twin-wheel bogies. Years later, this exact same unusual configuration would be borrowed for the Swedish Viggen and the Soviet Su-34 strike fighter. Because of these tall gear struts, the TSR-2 looked a lot like a long-legged heron while sitting on the tarmac. This comical effect only became more pronounced when the aircraft flew low passes with its gear down. The airframe itself was constructed primarily from conventional aluminum. However, high-strength titanium and lithium alloys were used in the most critical, high-stress areas. The wing-to-fuselage attachment points deserve special mention. Thanks to some brilliant engineering, they acted like shock absorbers to dampen aerodynamic flexing and vibrations. This did not just make the ride much smoother for the crew, even in extreme turbulence. It also significantly extended the airframe's service life by reducing metal fatigue. The cockpit was state-of-the-art for its time. The pilot and navigator sat in modern ejection seats. These allowed them to safely punch out even at extreme altitudes, up to just over 55,000 feet, and at speeds around 1,400 miles per hour. Notably, this was the very first British aircraft to feature a head-up display. This was a massive technological breakthrough back then. The cockpit windscreen was also heavily reinforced. This was absolutely critical for safe low-level flying, where the risk of bird strikes is extremely high. All the targeting and navigation avionics were integrated into a single, cutting-edge computer system. At its heart was a forward-looking multi-mode radar. Beyond the radar, the suite included advanced tech like inertial and Doppler navigation. It also featured an air data computer, a dual radar altimeter, and a highly capable autopilot. Interestingly, this autopilot was based on a proven American system already being used on the A-5 Vigilante. But British engineers heavily modified it specifically for their new bomber. The designers proudly claim this electronic suite allowed the aircraft to automatically fly terrain following profiles at an incredibly low altitude, just about 300 feet. At the same time, the system's margin of error was less than 100 feet. If the electronics ever failed, an automatic failsafe would instantly command a sudden pull-up. That gave the pilot precious seconds to safely take over manual control. Naturally, the aircraft carried all the latest secure radio communications, IFF systems, and precision instrument landing equipment. The aircraft's reconnaissance arsenal was just as impressive. 3 powerful cameras were housed right in the nose, 1 facing forward and 2 oblique cameras on the sides. Engineers were also planning to add a side-looking airborne radar and infrared sensors. But the real star of the recon package was an innovative electro-optical scanning system. It could clearly capture the ground below in broad daylight or complete darkness. The most groundbreaking feature was that the collected intel could be transmitted to a ground command post via a secure TV link in near real time. Interestingly, the TSR-2 lacked an internal cannon. Its primary firepower was housed inside a large internal weapons bay. This bay was capable of holding around 6,000 pounds of ordnance. It could easily accommodate nuclear payloads. These ranged from a heavy, high-yield strategic bomb to multiple tactical nuclear warheads. For conventional strike missions, the bomber was designed to carry standard iron bombs, unguided rockets, and Martel-guided missiles. This additional ordnance, along with external drop tanks, could be mounted on 4 underwing hardpoints. Designers also explored a buddy-to-buddy refueling concept. Using a dedicated aerial refueling pod, the TSR-2 could refuel other TSR-2s in midair. This was a capability Soviet engineers would not field on the Su-24 until 20 years later. Early estimates projected the aircraft's maximum combat payload at roughly 10,000 pounds. Today, however, many of its exact specs remain theoretical. Because the flight test program was canceled prematurely, a lot of the projected performance figures were never actually proven in the air. Because the TSR-2 was designed from the ground up as a complete weapon system, entirely new ground support infrastructure was developed right alongside it. This included automated diagnostic equipment that was revolutionary for the era. It also included specialized gear meant to drastically reduce turnaround times between combat sorties. Furthermore, the inclusion of an onboard auxiliary power unit, or APU, allowed crews to spool up the main systems without relying on external ground carts. This made the aircraft highly self-sufficient. The first prototype officially rolled out of the assembly hangar on March 4, 1964. But it was still a long way from its maiden flight. When technicians tried to install the engines, they ran into a major problem. The power plants physically did not fit inside the engine bays. The entire tail section had to be rapidly redesigned. Interestingly, this was not the first time the British aerospace industry built an airframe that could not fit its engines. A similar fitment issue plagued the early development of the Gloucester Meteor. These embarrassing mix-ups usually boiled down to a severe lack of coordination between the airframe designers and the engine manufacturers during the initial design phase. It was a stark reminder that even advanced Western engineering programs could suffer from major disconnects. Once the engines were finally mounted and ground testing began, another major issue emerged. This issue was severe vibration. Until an upgraded batch of engines was ready, engineers had to compromise. They did this by imposing strict limitations on the flight envelope. As Chief Test Pilot Roland Beaumont later recalled, these engine issues practically dictated the pace of the entire flight test program. To be fair, no matter where an aircraft is built, the power plant is almost always the biggest developmental hurdle. This is especially true when it is a clean sheet design meant for one specific airframe. The reason is simple. A jet engine is an incredibly complex piece of thermodynamic machinery. Forging reliable components that can withstand extreme thermal and mechanical stress is a demanding task. Then, getting all the engine control systems to work in perfect harmony is a massive challenge for any engineering team. Meanwhile, preparations for the first flight were facing serious delays and the clock was ticking. It turns out the Soviet Union was not the only country that liked to rush projects to meet important dates or holidays. September was fast approaching, and with it came the prestigious Farnborough Air Show. The British government really wanted to show off their new TSR-2 there. They wanted this even if it was just a quick flyby. However, those plans just were not meant to be. The initial ground tests involved high-speed taxi runs down the runway. These did not start until September 2nd. During those runs, they were testing the brakes and flight controls. For a solid week, the engineers struggled with the braking system, which kept dangerously overheating. It was not until September 20th and 21st, after a series of urgent modifications, that the brakes finally functioned properly. After that, the aircraft was officially cleared for its maiden flight. On September 27th, test pilot Ronald Beaumont teamed up with navigator Don Bowen for the new bomber's highly anticipated maiden flight. By the way, he was also the first pilot to fly the older TSR-1 Canberra. This was really more of a demonstration flight. Ongoing technical issues meant they had to put heavy restrictions on the flight envelope. The crew could not retract the landing gear. The engine intake control system did not work at all. Thrust was capped at 97%, and they did not even have an autopilot on board. But even with all those limitations, it was a huge win. It proved to the project's critics that the aircraft could actually fly, and that things were genuinely moving forward. After touching down, Ronald Beaumont admitted he was pleasantly surprised by just how smoothly this brand new bomber handled. Although during the flight itself, the crew had a genuine scare. They noticed thick, white streaks streaming off the wingtips. At first, they panicked. They thought they had a massive fuel leak coming from the wing tanks. But they soon realized it was a false alarm. Those white streaks were just standard wingtip vortices caused by the aircraft's highly swept wings. Once back on the ground, Ronald Beaumont gave management an ultimatum. The next time he stepped into that cockpit, it would only be after those problematic test engines were completely swapped out for upgraded ones. He and his navigator were absolutely done playing Russian roulette with their lives. Once the bomber finally got its upgraded power plants, flight testing resumed. This happened just in time for New Year's Eve on December 31st. But it did not take long to figure out that the landing gear was going to be the next major headache for this aircraft. The main gear caused severe airframe vibrations when extended. This made it incredibly difficult to control the aircraft on approach. On top of that, it flat out refused to retract properly into the fuselage. Engineers had to pour a massive amount of time into troubleshooting. It was not until the 10th test flight that they finally got the landing gear working reliably. The TSR-2 finally went supersonic during its 14th flight in February 1965, while heading to Wharton Air Base. During the acceleration run, Ronald B. Mott pushed the throttles to full military power and hit Mach 1.01, just over 760 miles per hour. That is exactly when they discovered that the afterburner on one of the engines refused to light. Despite the malfunction, he engaged the working engine's afterburner at 1/3 power. He still managed to push the heavy bomber up to Mach 1.12, or about 850 miles per hour. How is that for a textbook example of supercruise? From an aerodynamic standpoint, the bomber was practically flawless. Unfortunately, the same could not be said for its power plants and several onboard systems. The engines remained a constant headache for every engineer and pilot involved in the project. On top of that, the cockpit's environmental control system was dangerously inadequate. And once the aircraft started flying low-level profiles, serious fuel leaks became part of the problem. On February 26th, Roland B. Mott took the controls of the TSR-2 for the very last time. After that, Jimmy Dell took over testing duties. He had already flown the jet a few times by then. He would not be flying it for long, though. The bomber only managed to log 8 more test flights before its ultimate fate was sealed. In the end, the first prototype spent just 13 hours and 3 minutes in the air, completing exactly 24 sorties. The second prototype had even less luck. In September 1964, the airframe sustained serious damage while being towed into a hangar at Boscombe Down. Engineers spent months on repairs. The jet was not ready for its first flight until early April 1965. Ironically, on that exact long-awaited day, British Prime Minister Harold Wilson officially announced the cancellation of the new bomber program. Instead of sticking with a homegrown design, the government decided to purchase the American F-111. The decision came as a profound shock. It is still considered one of the darkest chapters in British aviation history. The government did not just pull the plug on the most advanced combat aircraft of its day. They crushed the future prospects of the country's entire aerospace industry. During the testing of the TSR-2, British engineers were gaining invaluable experience in developing a supersonic multi-role combat system. That kind of institutional knowledge and technology could not be bought at any price. Adding insult to injury, the British leadership eventually backed out of buying the American strike aircraft in January 1968. At the time, the F-111 was United States Secretary of Defense Robert McNamara's pet project. It was suffering from severe teething problems. On top of that, unit costs were skyrocketing out of control. This made the purchase a terrible financial deal. As a result of these political decisions, the Royal Air Force found itself without a modern strike aircraft. Lacking better alternatives, the British had to take a step back and revisit a decade-old design. They adopted the Buccaneer, operating it as a low-level strike bomber. It is worth pointing out that much later, during Operation Desert Storm, these aging airframes managed to partially redeem their reputation. They proved highly effective in combat. To plug the gap in their defenses, the United Kingdom also procured the already well-proven American F-4 Phantom. Today, aviation historians still struggle to explain why the British military did not take a closer look at the American A-5 Vigilante back then. The aircraft had a tremendous amount in common with the canceled TSR-2. This included its overall design, its internal bomb bay, and its very similar flight envelope. Most likely, the reason was that the American counterpart had a slower, low-level dash speed and a shorter combat radius compared to the British jet. For the RAF command, those specific performance metrics were absolutely critical. On top of that, the Americans themselves were far from thrilled with the Vigilante in the strike role. It simply did not live up to expectations. As for the TSR-2s themselves, they met a pretty grim fate. By the time the program was abruptly canceled, only 3 of the 9 planned airframes had been fully completed. The rest were in various stages of assembly. Between 1972 and 1973, any lingering hopes of reviving the project had finally evaporated. Almost all of these unique jets were systematically sold off for scrap. The last one to meet the scrapper's torch was the only TSR-2 that had actually taken to the skies. That heartbreaking loss for the aviation community happened in 1982. The second and fourth airframes fared a little better. The second prototype was saved from the chopping block. Today, it is a centerpiece on display at RAF Museum, Cosford. The other surviving airframe was later transferred to the Imperial War Museum at Duxford, where it remains on public display. On top of that, they miraculously managed to save the nose section of one of the unfinished airframes. You can go see it today at the Brooklands Museum. And that was the anticlimactic end to an incredibly ambitious program. Had it actually reached production, it would have firmly secured Great Britain's place at the forefront of military aviation for decades to come.